And now for part three of our video three, I should say, part three of the videos of uh, chapter 4.4, section 4.4. So example 12, we want to write this vector. Now, we already established in a previous example that these are linearly dependent, which means that one vector could be written as a linear combo of the other two. And in when we did this in example way back, just the last video, we did this problem. So we had C. So when we did this example, we had C1 V1 C2 V2 C3 V3 equals 0, and we got this system of equations. And we showed we showed through our magic that it has infinite solutions. Well, let's just suppose we would let C2 equal negative t. So this is equal to C1 minus 2t equals 0. Bring the minus 2t over to the other side, it becomes plus 2t. So C1 is now 2t, which is what we have right there. C1 is 2t. Once we know that C1 is 2t and C2 is negative t, this becomes 2 minus 5, which is negative 3t, plus C3 equals 0. Bring the negative 3 to the other side, it becomes positive 3, and we get C3 equals positive 3t. Now, once we have the parameters like this, we can plug in any value we want. Just for example, if we plug in t equals 1, really we can plug in any real number. That's infinite solutions. But if we plug in t equals 1, we get 2v1 minus v2 plus 3v3 equals 0. So I could let v2 just equal 2v1 plus 3v3. And if you want to check that, if you don't believe me, check it out, and you can check it out. But just go through this and just clarify this all works. So let's moving on. Actually, you can see it kind of well. Moving on. So 4.8 has a practical corollary, and it's a very simple test for whether two vectors are linearly dependent. And if two vectors, u and v, in a vector space, two vectors, u and v, in a vector space v are linearly dependent if and only if one is a scalar multiple of the other. So if I'm dealing with 3 or more vectors, this corollary doesn't apply. But if I'm just dealing with 2 vectors, then the only way 2 vectors are going to be linearly dependent is if one vector is a scalar multiple of the other vector. And this is, again, very hard to prove. You could do it as a meanwhile, let's some examples. So S is equal to V1, V2. So S is equal to 1, 2, 0, and negative 2, 2, 1. This is independent because these two vectors are not scalar multiples of each other. Whereas if I'm looking at these two vectors, V1, V2, 4, negative 2, and negative 2, 2, 1, they are dependent. I'm sorry, the first one is independent. They're dependent because if I take this second vector here, if I take this vector here, multiply it by negative 2, I get vector over there. So V1 is equal to negative 2 times V2. So they're, and this is just a graph of what they look like. So if you notice, the example for the first example, the two vectors were not collinear. The second example, the two vectors are collinear, and that is what we're trying to show. So it all works out beautifully. It's been a lot of fun, and we'll see you all in the next section, which is very fabulous and exciting.